When dealing with a multiple regression, we now have two covariates, both x1 and x2. So we have to interpret both beta 1 and beta 2. Beta 1 begins the same as it did in a bivariate regression, wherein a 1-unit increase in x1 is associated with a change in y of beta 1, but holding x2 constant. This is the key difference between bivariate and multivariate regressions. Similarly, beta 2 is a 1-unit increase in x2 is associated with a change in y of beta 2 holding x1 constant. This notion of holding variables constant also corresponds to the calculus. So, if we were to take the partial derivative of y with respect to x1, we would get beta 1, and a partial derivative of y with respect to x2, we would get beta 2. A partial derivative assumes that the other variables in the equation are being held constant. Now take a look at this sample regression function. Y still corresponds to test scores as before, and x1 still corresponds to student-teacher ratios, but now we have an additional covariate, average income. Beta 1 hat corresponds to the coefficient in the data output, and beta 2 hat corresponds to this next coefficient. Though this is a multiple regression, our significance tests on each coefficient is still simply a t-test. So, for beta 1, our null hypothesis is that beta 1 equals 0, and we have a corresponding t-statistic of negative 1.84 and a p-value of 0.067. Similarly, the null hypothesis for beta 2 is that beta 2 equals 0. We have a t-statistic of 16.03 and a p-value of less than 0.0001.